there is something unexpected on the moon. Something scientists didn't predict would be there. On August 23, 2023, India's Chandrayaan 3 mission touched down near the lunar South Pole, the first spacecraft in human history to land in this remote, mysterious region. Within days, the mission discovered something that would rewrite our understanding of the moon's formation. Not water. Something that tells a story 4.5 billion years in the making. This is what India found on the south pole of the moon. The mission was called Chandrayaan 3, the third in India's Chandrayaan program, a Sanskrit word meaning moon vehicle. It launched on July 14, 2023, from the Satish Dhawan Space Center in Sriharikota, India, aboard a launch vehicle Mark III rocket. The spacecraft consisted of 3 components: a propulsion module, a lander named Vikram, and a 6-wheeled rover named Pragyan, meaning wisdom in Sanskrit. The target was 69 degrees south latitude, the lunar South Pole region, a place no lander had ever reached before. The terrain there is brutal, craters hundreds of miles wide, boulders scattered across steep slopes, shadows that stretch for billions of years, never touched by sunlight. But that's exactly why scientists wanted to go there. Because where there is shadow, there could be water ice. Where there is water ice, there could be the building blocks for future human exploration. That was the expectation: water. But what the rover found sitting in the regolith, the dusty lunar soil, was something far older and far more revealing. On August 5th, the spacecraft entered lunar orbit. On August 17th, the Vikram lander separated from the propulsion module. Then came the descent. At 30 kilometers above the surface, Vikram fired its 4 engines as a braking maneuver. For 11.5 minutes, it fell toward the moon. At 7 kilometers, the lander stabilized using 8 smaller thrusters. It rotated from horizontal to vertical. At 150 meters, it hovered, searching for a safe spot to land. Then it descended. August 23, 2023. India became first to land near the South Pole. Within hours, the Pragyan rover rolled down a ramp from Vikram's belly and onto the lunar surface. Its mission: explore for 14 Earth days, 1 lunar day before the brutal lunar night would freeze its electronics at -120 degrees Celsius. The rover carried 2 instruments designed to analyze the composition of the moon: an alpha particle X-ray spectrometer and a laser-induced breakdown spectroscope, known as LIBS. On August 25, just 2 days after landing, the rover began firing its laser at the lunar soil. That's when the discovery began. The first target was simple: measure what elements are present in the regolith. The laser works by firing a high-energy pulse onto rock or soil. The pulse generates an extremely hot and localized plasma, essentially vaporizing a tiny piece of the surface. That plasma emits light. Different elements emit different wavelengths of light. By analyzing the spectrum, you can identify exactly what the material is made of. On August 29, 2023, the Indian Space Research Organization ISRO released the first results. The rover had detected sulphur. This was the first ever in situ confirmation of sulphur near the lunar South Pole. Sulphur had been detected before by orbiters using remote sensing, but this was different. This was direct measurement, surface contact, ground truth. But sulphur wasn't the only thing the rover found. The LIBS instrument revealed a full elemental profile: aluminum, calcium, iron, chromium, titanium, manganese, silicon, oxygen, and further measurements revealed the presence of sulphur at concentrations higher than expected, much higher. Now, here's where it gets interesting. Sulphur on the moon is primarily associated with volcanic activity. Deep inside the moon, rocks contain sulphur. When those rocks melt and rise to the surface as magma, most of the sulphur becomes a gas and is released along with water vapor and carbon dioxide. Some sulphur stays in the magma and is retained in the rock after it cools. This is why sulphur is found in the moon's dark volcanic plains, the Maria, which are made of basalt. But the South Pole isn't volcanic terrain, it's highland terrain. Bright, ancient, heavily cratered. Highland soils are typically lower in sulphur than the dark volcanic regions. And yet, the uncalibrated data suggested that the highland soils near the poles might have a higher sulphur concentration than highland soils at the equator, possibly even higher than the dark volcanic soils. That shouldn't happen, unless something else is going on. To understand what India found, we need to go back 4.5 billion years, when the moon formed. The leading theory is called the lunar magma ocean hypothesis. Here's how it works. About 4.5 billion years ago, a Mars-sized body called Theia collided with the early Earth. The impact was catastrophic. Material from both Theia and Earth was ejected into orbit. That material coalesced to form the moon. When the moon first formed, it was molten, a ball of liquid rock. This is the magma ocean. Over millions of years, the moon began to cool. As it cooled, minerals started to crystallize out of the magma the way ice crystals form when water freezes. Heavier minerals, like olivine and pyroxene, sank. Lighter minerals floated to the surface. One of those lighter minerals was called ferroan anorthosite. It's made primarily of a mineral called plagioclase feldspar, rich in aluminum and calcium. Ferroan anorthosite is less dense than the surrounding magma, so it rose to the surface and solidified, forming the moon's ancient highland crust. This theory has been around for decades, but it was mostly based on samples from the Apollo missions, which landed near the equator in the mid-latitudes. No one had ever tested the lunar magma ocean hypothesis at the South Pole, until now. In a paper published in Nature on March 6, 2025, the Chandrayaan-3 team presented their findings. Using the alpha particle X-ray spectrometer aboard the Pragyan rover, they conducted 23 measurements at 70 degrees south latitude. They found clear, unambiguous evidence of ferroan anorthosite. The signature was unmistakable: high concentrations of aluminum and calcium, low concentrations of iron and magnesium. Exactly what you'd expect if the ancient crust floated to the surface from a magma ocean. This was the first time ferroan anorthosite had been confirmed near the lunar South Pole. It means the lunar magma ocean wasn't just a regional phenomenon, it covered the entire moon. According to Dr. Santosh Vadawale, co-author of the study and scientist at India's Physical Research Laboratory, the findings make the theory of the moon's early evolution much more robust. Before Chandrayaan-3, the main evidence for the magma ocean came from the Apollo samples, collected from mid-latitude regions. Now, with in-situ confirmation from the South Pole, the picture is complete. The moon, at birth, was a molten sphere. It cooled, it crystallized, and what we see today, the bright highlands, is the frozen remnant of that ancient ocean. But there's more. The team also found evidence of a massive impact, not the impact that formed the moon. A second impact, 4 billion years ago. The South Pole region sits near one of the largest impact structures in the solar system, the South Pole Aitken Basin. It's a giant crater, 2,500 kilometers across, roughly the distance from New York to Denver, about 350 kilometers from where Pragyan landed. 4 billion years ago, an asteroid slammed into the moon with unimaginable force. The impact excavated material from deep within the moon, possibly from the mantle, and threw it across the surface. Chandrayaan-3's instruments detected elevated concentrations of magnesium in the regolith. Magnesium is not abundant in the highland crust, but it is abundant in the mantle. The team believes this magnesium was ejected from the South Pole Aitken Basin during the impact and deposited across the surrounding region. Think of it like an explosion in a mine. The blast throws up material from deep underground, scattering it across the surface. That's what happened here. 4 billion years ago. The magnesium Pragyan detected is a fingerprint of that ancient collision. It's a direct sample of the moon's interior delivered to the surface by violence. This is significant for several reasons. First, it gives scientists a rare glimpse into the moon's subsurface composition without drilling. Second, it helps constrain models of how the moon's interior is structured, how thick the crust is, how deep the mantle begins. Third, It provides a natural laboratory for studying impact processes, how energy is distributed, how material is transported, how surfaces respond to catastrophic collisions. The moon's surface is not just old rock, it's a geological archive. Every crater, every boulder, every grain of dust carries information about the moon's history. And now, thanks to Chandrayaan-3, we have a new page in that archive. But let's return to the sulphur. The presence of sulphur at elevated concentrations near the South Pole is still puzzling. Here are a few possibilities. Possibility 1. Ancient volcanic activity. Perhaps volcanic eruptions occurred near the South Pole billions of years ago, depositing sulfur-rich material. But the region doesn't show obvious signs of recent volcanism. The terrain is ancient highland crust, not volcanic plains. Possibility 2. Impact-delivered sulphur. Meteorites contain sulphur. When they strike the moon, they vaporize on impact. The vapor can condense and settle across the surface. If the South Pole experienced more impacts, or if the impacts were sulfur-rich meteorites, this could explain the elevated concentrations. Possibility 3. Atmospheric sulfur deposition. The moon has an exosphere, an extremely thin atmosphere made of sparse gas molecules. Sulfur could be present in this exosphere, possibly released from volcanic outgassing billions of years ago, or from impacts. At the poles, where temperatures drop below -173 degrees Celsius, sulfur from the atmosphere could condense onto the surface like frost on a window. This process is called cold trapping. If sulfur is being cold trapped at the poles, it would accumulate over billions of years, leading to higher concentrations. The Chandrayaan-3 team suspects a combination of all three mechanisms: ancient volcanism, impact delivery, atmospheric deposition. Together, they create the sulfur-rich environment Pragyan observed. But the exact proportions remain uncertain, and there's another detail worth mentioning. The Chandrayaan-3 lander, Vikram, landed on a slope, not a flat plain, a 6-degree sunward-facing slope. This affected the temperatures measured by another instrument on board called CHASTI, Chandra's Surface Thermophysical Experiment. CHASTI was designed to measure how heat moves through the lunar soil. It inserted a probe 10 centimeters into the ground, equipped with 10 temperature sensors. The surface peak temperature measured was 355 Kelvin, about 82 degrees Celsius. This was 25 Kelvin higher than expected. The reason? The slope. On a flat surface, the peak temperature would have been around 332 Kelvin. But the slope angled toward the sun, receiving more direct sunlight. This small difference in angle created a significant difference in temperature. It's a reminder of how local topography matters on the moon. A few degrees of tilt can mean the difference between ice and no ice, between habitable and uninhabitable. Let's step back for a moment. What does all of this mean? Chandrayaan-3 confirmed that the moon's south pole is made of ancient highland crust, the frozen remnant of a magma ocean that covered the entire moon 4.5 billion years ago. This strengthens the lunar magma ocean hypothesis and provides the first ground truth data from the polar regions. It also detected magnesium-rich material, likely ejected from the South Pole Aitken Basin impact 4 billion years ago. This gives scientists a direct sample of the moon's interior without drilling, and it found elevated concentrations of sulfur, possibly due to a combination of ancient volcanism, meteorite impacts, and atmospheric deposition over billions of years. But beyond the science, there's something else: water. Remember, the original goal of Chandrayaan-3 was to search for water ice. And while the mission didn't directly detect water during its 14-day surface operations, the findings suggest where water might exist. CHASTI's temperature measurements revealed that slopes facing away from the sun, poleward slopes, can be cold enough to trap water ice just below the surface. Specifically, slopes with angles greater than 14 degrees may harbor subsurface ice deposits. This is important for future missions. If water ice is accessible at shallow depths on poleward slopes, it could be extracted for use by astronauts. Water can be split into hydrogen and oxygen. Oxygen for breathing, hydrogen for fuel. This is called in situ resource utilization, using local materials instead of bringing everything from Earth. It makes long-term lunar exploration feasible, and it makes the South Pole a prime target for future crewed missions. NASA's Artemis program is planning to send astronauts to the South Pole in the coming years. India plans to launch Chandrayaan 4 inches 2027, a sample return mission that will bring lunar soil back to Earth for detailed analysis. China, Russia, Japan, and private companies are all planning missions to the Moon's polar regions. The race is on, but it's not just a race for flags and bragging rights. It's a race to understand. To learn how planets form, how magma oceans crystallize, how impacts reshape surfaces, how volatile elements move through space. The Moon is a laboratory, a library written in stone, and every mission adds a new chapter. Chandrayaan 3 didn't just analyze the surface. It measured other aspects of the lunar environment, plasma measurements. The lander carried an instrument called Rambar LP, Radio Anatomy of Moonbound, Hypersensitive Ionosphere and Atmosphere, Langmuir probe. It measured the density of charged particles plasma above the lunar surface. The probe detected electron densities between 380 and 600 electrons per cubic centimeter, with kinetic temperatures ranging from 3000 to 8000 Kelvin. This was significantly higher than estimates from orbital observations. It suggests the lunar surface has a more active electrical environment than previously thought. This matters for future missions because charged particles can affect electronics and pose risks to astronauts. Understanding the plasma environment helps engineers design better spacecraft and habitats. Seismic measurements. Another instrument, ILSA, Instrument for Lunar Seismic Activity, was designed to detect moonquakes. It recorded vibrations from the rover's movement and other lander operations. On August 26, 2023, ILSA detected an event that appeared to be natural. The source is still under investigation. It could have been a moonquake caused by tectonic stress or thermal expansion as the lunar surface heats and cools. Or it could have been a small meteorite impact, or something else entirely. The data is being analyzed. But the fact that ILSA operated successfully proves that seismology is possible on the Moon, and that future missions could use networks of seismometers to map the Moon's interior structure, just as seismology on Earth revealed the structure of our planet's core, mantle, and crust. Thermal measurements. Chasti provided unprecedented detail on how temperature varies with depth. At 9 o'clock lunar local time, the temperature difference between the surface and 10 centimeters depth was 62 Kelvin. By 3 o'clock in the afternoon, the difference had decreased to 36.5 Kelvin. This tells us how heat moves through the regolith. It tells us about the thermal properties of lunar soil, its conductivity, its capacity to store heat, and it tells us where ice could survive. Below a certain depth, temperatures remain stable. If ice is buried beneath the surface, protected by a layer of dry regolith, it could remain frozen for billions of years, even in sunlit regions. This is one of the most important discoveries for future exploration, because it means water ice could be more widespread than expected. Not just in permanently shadowed craters, but beneath the surface, hidden, waiting. Chandrayaan 3 was not just a scientific mission, it was an engineering demonstration. India proved it could land on the Moon. In one of the most challenging environments in the solar system, the mission also performed a hop experiment. On September 3, 2023, Vikram fired its engines and lifted off the surface. It ascended 40 centimeters, translated laterally a similar distance, then landed again, safely. This was a test of technologies needed for future sample return missions. The ability to take off from the Moon, carry samples to orbit, and return them to Earth. India plans to do exactly that with Chandrayaan 4. Launch, land, collect samples, return. The HOP experiment proved the engines work, the control systems work, the navigation works. It's a small step, but it's a critical one, because every future mission, whether robotic or crewed, will require these capabilities. The mission lasted 14 Earth days, 1 lunar day. On September 4th, 2023, as the sun set over Statio Shiv Shakti, the lander and rover entered sleep mode. Their batteries were charged, their receivers were left on, but the temperature was dropping, -120 degrees Celsius. Too cold for the electronics to survive. On September 22nd, ISRO attempted to wake the lander and rover. No response. On September 28th, they tried again. Still nothing. The mission was over, but the propulsion module was still in orbit, still operational, and ISRO decided to use it. After the lander mission concluded, the propulsion module had over 100 kilograms of fuel left. Instead of letting it drift in lunar orbit, ISRO's flight dynamics team planned a series of maneuvers to return it to Earth orbit. On October 9th, 2023, they raised the module's apogee from 150 kilometers to 5,112 kilometers. On October 13th, they performed a trans-Earth injection. The module performed 4 lunar flybys. On November 10th, it exited the Moon's sphere of influence. On November 22, 2023, it crossed perigee at an altitude of about 154,000 kilometers above Earth. It is now in a high Earth orbit. Perigee altitude varies, but the minimum is about 115,000 kilometers. Orbital period, nearly 13 days. Inclination, 27 degrees. The module carries a scientific instrument called SHAPE, Spectropolarimetry of Habitable Planet Earth. It studies Earth's spectral and polarimetric properties in near-infrared wavelengths. The goal is to understand how Earth would appear to distant observers searching for habitable planets around other stars. This is called exoplanet research. By studying Earth as if it were an exoplanet, scientists can develop better methods for detecting biosignatures, signs of life on planets orbiting distant stars. SHAPE continues to operate. The propulsion module remains in service, and the data keeps coming. Chandrayaan 3's success did not go unnoticed. The mission received international recognition. In 2023, ISRO was awarded the Leif Erikson Lunar Prize by the Exploration Museum for dedication and advancements in lunar exploration. In 2024, ISRO received the Aviation Week Laureates Award for the Chandrayaan 3 mission. The mission team was awarded the John L. Jack Swigert Jr. Award for Space Exploration, presented at the annual Space Symposium in Colorado on April 8, 2024. In October 2024, the International Astronautical Federation presented Chandrayaan 3 with the World Space Award. The award was presented at the 75th International Astronautical Congress in Milan. According to the International Astronautical Federation, Chandrayaan 3 exemplifies the synergy of scientific curiosity and cost-effective engineering. The mission cost about 615 crore rupees, roughly $86 million. For comparison, a single Hollywood blockbuster can cost more. This was done through local sourcing, efficient design, and careful planning. India proved that lunar exploration doesn't require unlimited budgets. It requires ingenuity, dedication, and the will to explore. So what have we learned? That the moon was once molten, that impacts can deliver material from the deep interior to the surface, that sulphur exists at the poles in higher concentrations than expected. That temperature varies dramatically. With slope angle, just a few degrees can make the difference between ice and no ice. That water ice may be buried beneath the surface in more locations than previously thought. That the moon's plasma environment is more active than models predicted. That seismology is possible on the moon. That India can land softly, explore scientifically, and return data that changes our understanding of the solar system. But perhaps the most important lesson is this: the moon is not finished revealing its secrets. Every mission uncovers something new, and every discovery raises new questions. How much water ice is really there? What caused the elevated sulfur concentrations? Are there other regions with similar compositions? Can we extract resources sustainably? Can humans live there long-term? These are the questions driving the next generation of missions. Chandrayaan 4. Artemis. The moon is becoming a destination, not just for robots, but for people. And the data from Chandrayaan-3, the ferroan anorthosite, the sulphur, the temperature profiles, the plasma measurements, the seismic signals, all of it will guide those missions. It will inform where to land. On August 23, 2023, India joined an elite group of nations: the United States, the Soviet Union, China, and now India. Countries that have touched the moon. But Chandrayaan-3 did more than touch. It explored, it confirmed a theory that has existed for decades, the lunar magma ocean hypothesis, with direct, in situ evidence from the South Pole. It found sulphur in concentrations higher than expected. And it proved that lunar exploration is not the domain of superpowers alone. Any nation with vision, skill, and determination can reach the moon. India did, and the world is better for it, because every mission expands our knowledge. Every landing adds to the map. And every discovery brings us closer to understanding where we came from, how the moon formed. The moon is a witness to 4.5 billion years of solar system history, and we are only beginning to read its testimony. Chandrayaan-3 turned the page. What comes next is still being written. For now, the data is here, the discoveries are real, and the moon, once thought to be a dead world, is proving to be far more complex, far more dynamic, and far more important than anyone imagined. India found something on the South Pole, not just water, not just ice, but the frozen memory of an ancient ocean, a magma ocean, the birth of the moon itself, what we know so far. The moon's South Pole contains ferroan anorthosite evidence of a global magma ocean 4.5 billion years ago. Sulphur is present in elevated concentrations, likely due to a combination of ancient volcanism, meteorite impacts, and atmospheric deposition. Magnesium-rich material ejected from the South Pole Aitken Basin 4 billion years ago is present in the regolith. Temperature varies significantly with slope angle. Poleward slopes greater than 14 degrees may harbor subsurface water ice. The lunar plasma environment is more active than expected. Seismology on the moon is possible. Chandrayaan-3 successfully demonstrated soft landing, roving, and hop capabilities. Here's what the data suggests. Water ice may be more widespread than previously thought, buried beneath the surface in many locations. The moon's crust is compositionally uniform from the equator to the poles, supporting the lunar magma ocean hypothesis. Future missions should target poleward slopes for resource extraction. In situ resource utilization is feasible. Long-term lunar exploration is possible with careful planning. What if we're only beginning to understand the moon? What if every mission reveals something unexpected? What if the moon, quiet, airless, seemingly dead, is actually one of the most scientifically rich bodies in the solar system? That's the question Chandrayaan-3 has left us with, and the answer will come from the next mission, and the one after that. The moon is waiting.